Thanks for watching my video. My name is Lin Yang. I'm from the University of Massachusetts at Amherst. I'm a postdoc there and working with Professor Dan Tosley and Mohammed Hajj. My research interests cover several fundamental areas in computer science, including online learning and online optimization. In this talk, I will introduce a piece of work of mine on multi-scale learning strategy and the classic expert model. Now let me start my presentation. The title of my today's presentation is Hierarchical Learning Algorithms for Multi-Scale Expert Problems. This is a joint work, and the collaborators include Janice Yujen Chen, Mohammed Hajj, Mark Herbster, and Dan Tosley. Mark Herbster is from University College London, and the others are from the University of Massachusetts at Amherst. First, let me introduce the problem that we studied, that is the so-called multi-scale expert problem. Before I introduce our problem, I would like to first introduce the traditional model of the expert problem, that is the Hedge model. In the Hedge model, the learner is required to make sequential decisions from a given set of experts. Associated to each expert, there are a series of rewards, which are adversarial and do not subject to any fixed distribution. In the basic setting of the expert problem, we assume uniform reward ranges of the expert, for example, from 0 to 1. After the learner commits to one decision, she will receive the reward associated to the selected expert. The Hedge model assumes full information feedback. That means the learner will observe all rewards after her decisions at each decision round. The reward observed by the learner can be used to learn the best expert and update her future selection policy. The goal of the learner is to convert her decisions to the best expert, and thus her performance can be measured by the so-called pseudo-regret, which is defined as the difference of the cumulative reward of the best expert and that received by the algorithm. This problem has a research history of more than 20 years, and in our work, we study a more general case with non-uniform reward ranges. In the next slide, I will talk about the related results for both the basic expert problem and the multi-scale version. So specifically, I will show that there are few theoretical results for the general case with non-uniform reward ranges. To introduce the results, I will assume that there are totally capital K experts and capital K decision rounds. For the Hedge model, the classic exponential weighting algorithm or the Hedge algorithm can attain a regret of square root of capital T log K. This regret is optimal, and it matches the lower bound for the basic version of the expert problem. The optimal result for the multi-scale case is still open, and actually we only have several simple results for the general case. For example, we assume the largest reward upper bound is capital U, then applying the classic Hedge algorithm can lead to a straightforward regret, which is capital U times square root of capital T log K. Another recent work by Bobek proposed a novel algorithm which can attain a regret which depends on the upper bound of the best expert instead of the largest one. This improves the result of the Hedge algorithm in some cases. However, in the worst case, where the best expert has the largest upper bound, their result will reduce to the regret of the Hedge algorithm in the multi-scale expert case. Okay, these are the related results for the multi-scale expert problem. And in this slide, I will show our result. So specifically, without a loss of generality, we assume that the upper bounds of the experts are in a descending order, which are capital U1, capital U2, and so on. By applying a hierarchical learning structure to our learning algorithm, we can attain the following regret as shown in this slide. This regret function actually is a function of the upper bounds of the experts, and it's a little bit complicated. Here, I want to share two messages to you. First, the experts with small upper bounds will make small contributions to our regret, and therefore the result of our algorithm is very meaningful, especially for the applications where there are lots of For example, infinitesimal experts with very small reward upper bounds. The second message is that the requirement of our algorithm depends on the hierarchical learning structure tailored for the specific expert upper bounds. And the requirement shown in this slide actually is a looser upper bound, which is obtained by some specific learning structure. By optimizing the structure for given upper bounds, we can have a much better regret result. And I will show this in the following slide by using several examples. Okay, let's look at the examples. In this slide, we have two examples. In the first one, we have two groups of experts. In the first group, we have an expert with a larger upper bound, which is capital U. Capital U is larger than 1. In the second group, we have multiple experts, which has the upper bound 1. For this example, our algorithm can get the following regret, which is much better than the traditional algorithm. Specifically, the regret is in the order of square root of capital UT plus square root of capital T log K minus 1. You can find that our regret has much better dependency on the upper bounds of the experts. In the second example, we assume that the upper bounds of the experts decrease exponentially with a factor A. A is smaller than 1. Compared to the traditional regret, our results can totally drop the dependency on the number of the experts, and thus it improves the current result significantly, especially for the case with many infinitesimal experts with small reward upper bounds. In addition, in our work, we show that both results are optimal for the examples, and those results are obtained by using some specific learning structures, and I will show this later on in our introduction to the algorithm. Okay, now let's look at the algorithm that we have proposed. Okay, before I introduce the algorithm, I would like to introduce several iterations. So basically, characterizing the experts with similar upper bounds and implementing differentiated learning algorithms for each subset of experts can improve the performance of the learning algorithm, especially when the experts are multi-scale. This method can lead to a hierarchical learning structure for the algorithm. For example, to implement the above idea of categorizing experts, in our algorithm, we design a decision tree by partitioning the expert set into two smaller subsets recursively. Specifically, the whole set of the experts resides in the root of the tree. With the decision tree, to make a decision at each time slot, the learning algorithm has to select the children of the nodes from the root to some leaf. Actually, according to the hierarchical learning tree structure, the proposed learning algorithm has to solve a series of two expert problems from the top layer to the bottom layer. In addition, the leaf node may contain multiple experts if some experts have similar upper bounds, since in this case, we don't need to partition them anymore. If the selected leaf contains multiple experts, the learning algorithm will continue to select an expert in the leaf node as a final decision. And since the experts in the leaf node has similar upper bounds, and so at the last step, we can apply the classic, for example, exponential weighting or the hedge algorithm to select an expert. Okay, this is the first part of our algorithm. In this part, we construct a learning structure for the algorithm. Given the hierarchical learning structure, another important part of the algorithm is to select a child node for each at each layer. For each two expert problem, where the child node is taken as the expert, super expert, we adopt a randomized algorithm by which we generate the selection probability of the expert with a smaller cumulative reward by the following equations. In the equations, capital LT is the gap of the cumulative rewards between the two experts, and eta is a positive algorithm parameter. Apparently, the larger the gap, the smaller the selection probability for the expert with the smaller cumulative reward. In addition, the learning rate determines the speed that the algorithm converges to the better expert. With non-uniform reward ranges, the learning rate should be optimized for better performance. And here we have several examples. For example, specifically, an important observation is that the experts with different upper bounds actually contribute differently to the regret of the algorithm. For example, if the expert with the larger reward upper bound has a larger cumulative reward, it will take longer for the other expert to catch up with it. Thus, the algorithm in this case will be more confident to select the expert with the larger cumulative reward. So in this case, an aggressive or larger learning rate should be configured for the selection probability. On the other hand, when the expert with smaller upper bound predicts larger cumulative reward, as shown in the figure on the right-hand side, the other expert falling behind may catch up quickly, and the learning rate in this case should be set conservative. By properly setting the learning rate according to different cases, the node algorithm can work well in selecting a child. Okay, so this is the second part of our algorithm. Okay, now let's move further to look at the last part. As I have mentioned, each node in the structure solves an independent two-expert problem, and the performance of each node in selecting the better child can be measured by the so-called node regret. The node regret depends on the upper bounds of the content expert in the node. The total regret of the algorithm is equal to the summation of the node regrets from the path from the root to the leaf containing the optimal expert I star. It is straightforward that the total regret of the algorithm is not only dependent on the upper bounds of the experts, but also the hierarchical structure of the learning algorithm. So to have a better performance, we should also optimize the structure of our algorithm. In our work, we also provide a method on how to optimize the tree structure based on the upper bounds of the experts. And we show that the upper bounds of the experts may lead to much different structures of the trees. For example, I have shown two examples for which we design the optimal algorithm and obtain the optimal regret. And here are the optimal structures for the two examples respectively. Okay, up to now I have introduced the results of our algorithm and the details. And we also ran simulations to evaluate the performance of our algorithm. Here are the setups of our simulations. Generally, we consider 8 experts whose rewards subject to Bernoulli processes. We ran the algorithms for 3,000 rounds and generate each data point by 10 trials. In our experiments, we compare our algorithm to 3 baseline algorithms. The first one is a hedge algorithm, which is a basic algorithm for the traditional expert problem with uniform reward ranges. The second one is an advanced version of the hedge algorithm, which can tune its learning rate based on the empirical reward ranges of the experts. The last one is by the work of Bobek, which is designed for the multi-scale expert problem. Remember that the regret of Bobek's algorithm depends on the upper bound of the best expert. Okay, in our simulation, we designed 2 experiments. In the first one, we categorized the experts into 2 groups, each of which has 4 experts. The first group of experts have a uniform reward range from 0 to 1. In this experiment, we varied the reward upper bounds of the experts in the second group from 2 to 6. The means of all experts are randomly selected from 0 to 1, but we assume that the optimal expert lies in the first group. With different upper bounds of the second group, the regrets of the algorithms, including our algorithm and the baseline algorithms, are shown in the figure on the right-hand side. From the figure, we can find that except our algorithm, the advanced hedge algorithm and the MSMW algorithm also work very well. The explanation is as follows. First, the regret of the advanced hedge algorithm is based on the actual reward ranges of the experts. So with reward means less than 1 in both groups, it can achieve a very good regret. Also, for the MSMW algorithm, it can work very well, especially when the optimal expert lies in the first group, because its regret bases on the upper bound of the best expert. And here are our explanations. To verify our observations, we put the best expert into the second group and run another experiment. And in this experiment, we put the optimal expert in the second group, and from the figure, we can find that the regret of the MW algorithm also gets worse. Okay, this is the first experiment. In the first experiment, we set the reward means in both groups less than 1. So the advanced hedge algorithm works very well since the effective reward ranges of the experts are very small. In this experiment, we remove the constraints on the reward means and select the reward means in both groups randomly from the reward ranges. And the other setups are the same as the first experiment. In this, we also plot a figure to show the regret of our algorithm and the baseline algorithms. From the figure, we can find that the advanced hedge algorithms also suffer severe performance degradation. So by using the two experiments, we can show the advantages of our algorithm, and our algorithm can work very well for the general case with non-uniform reward ranges. Okay, after now I have finished my presentation. Thanks again for watching my video.